We start a new chapter today, and as you can see, today we're going to be introducing you, in some cases, refamiliarizing you with some trig identities, and then we're going to introduce you to some new ones. And these identities, just think of these as trigonomic truth statements that we can use to help us simplify problems. And that's going to be the objective for today. As you can see, we're going to be using these identities to find trig values, and sometimes these trig values are going to be involved. They're going to have to be broken down from more complex trig expressions. And so these identities are going to be helpful to take more complicated expressions and breaking them down into simple trig values. So that's the overall objectives for today. And so let's get started with a review of some identities that we've already seen. We would consider all of these to be basic trig identities. These quotient identities we've already looked at. We've talked about how that you can make tangent by doing sine divided by cosine. We also mentioned dealing with the unit circle, that if you take the y coordinate of a point on the unit circle from an ordered pair and you divide by x, you can also get tangent in that way. And then the reciprocal of cotangent, of course, or tangent is cotangent, and so that's another quotient identity if you do cosine divided by sine. All of these assume that the denominator cannot be zero. Of course, you can't divide by zero. And we've already looked at all of the reciprocals. We know that sine and cosecant are reciprocals of each other. So we can say that sine is the same thing as 1 over cosecant. That's just another way of saying the reciprocal of 8 is 1 over 8. And it works the other way around, of course. Cosecant is the same thing as 1 over sine. So I don't think these are anything new. We introduced all of these back in lesson 9.1 when we started doing right triangle trig. And so I'm going to go through these, just touch on them. And I really want to get to this new set of identities called the Pythagorean identities. And I'm interested in you being able to derive these Pythagorean identities and look at how you can come up with other what I call spin-offs of these three main Pythagorean identities. So to begin with, if you're wanting to derive these yourself, just make yourself a right triangle and place theta in either one of these acute angles. Really doesn't matter which. So in my example, of course, I've got theta down here in the bottom right. And since these are Pythagorean identities, they are derived, you probably guessed it, from the Pythagorean theorem. So the way we get these identities is we divide one at a time. We're going to do 3 different divisions, and we're going to divide by each of these parts of the Pythagorean theorem formula one at a time. So let's start by dividing by c squared. If I take c squared and I divide all the way across into the Pythagorean theorem, what is the result in terms of trig functions, thinking again relating to where theta is placed? Okay, so going to my triangle, I see the A side is called the adjacent side to theta. C, of course, is the hypotenuse, and the ratio of adjacent over hypotenuse is cosine. So instead of saying a squared over c squared, relating it to this triangle, I can say cosine squared theta. Okay, and then this fraction says b divided by c, and when we relate that to theta, that's the opposite side of theta divided by the hypotenuse, and we remember that opposite over hypotenuse is another way of saying sine squared theta. The reason why these trig functions are squared is because both of these are squared. And then anything divided by itself, c squared divided by c squared is just 1. So that is one of our Pythagorean identities, and from that we can come up with other versions, or again, you can think of them as spin-offs. We can solve for each of these, either cosine or sine, just by subtracting the other one. So it's also true based on this blue Pythagorean identity that we just came up with. It's also true that cosine theta is the same thing as 1 minus sine squared theta. And in like manner, it's true that sine squared theta is the same thing as 1 minus cosine squared theta. So pretty simple. All we did to solve for each of these is subtract the other one from both sides. Okay, so we might call this one the main Pythagorean identity, and from that we derive these other two sub-identities, if you want to think of them that way. Okay, so now let's come up with another Pythagorean identity, and this time just pick one of these to divide by. Let's just say we divide by a squared. Okay, so I'll go back and put the Pythagorean theorem back, and we'll do division by a squared this time. And we want to know what comes out of this in terms of trig functions. Okay, well, a squared divided by a squared is just 1. And then side B, back to my right triangle, side B divided by side A. Well, we usually say opposite over adjacent, okay? And we have described for theta, the opposite side over the adjacent side is called tangent. So B squared over A squared would be tangent squared theta. And then the side C, which is the hypotenuse divided by A, that's the reciprocal of cosine. Cosine is adjacent over hypotenuse. Well, this is the flip of that. This is hypotenuse over adjacent squared. So the reciprocal function for cosine is called secant, and it would be squared. Okay, and so that's Pythagorean identity. If they don't really have numbers, but we'll call this number 2. And then, of course, you can solve, it's already solved for secant squared, but if you wanted to solve for tangent squared, you would just subtract 1, just like we did up here. So we can go ahead and just say that tangent squared theta is the same thing as secant squared theta minus 1. All right, and then finally, the third, we haven't divided through by b squared yet, so let me put the Pythagorean theorem back. And this time we'll divide everything by b squared. And what does that result in terms of trig functions? So a side divided by b side. All right, so opposite over adjacent, of course, is tangent, but this is adjacent over opposite, so that's going to be cotangent squared theta. And then, of course, this is plus 1. And then c over b, well, we're used to seeing b over c. That's opposite over hypotenuse. That's sine. So c over b must be the reciprocal for sine, which is cosecant. And so once again, we have another Pythagorean identity. So I'm just going to circle these 3. And then hopefully you see how you can manipulate them to solve for other trig functions within those identities just by subtracting. So I could solve again, I won't write it up, but I could solve for cotangent squared by subtracting 1. So cotangent squared theta is the same thing as cosecant squared theta minus 1. Okay, and you're going to get some practice with these today as you do your homework problems, and that's the whole intention, is to force you to use all, as much as needed, use trig identities to simplify, come up with your final answer. We've got these co-function identities. Some books refer to this as the complementary angle theorem. Let's write this up just in case you see it later in another class. It really means the same thing. Complementary angles add together to equal 90 degrees. And so I know this maybe looks a little confusing to some people, this mathese, but really this is just stating a complementary angle. Pi over 2 is just 90 degrees. So 90 minus some angle theta. Okay, so maybe I'll put a number in here for theta. What if we just arbitrarily said that theta is 30 degrees? Okay, so this would be 90 minus 30, which is 60. So that would make sine 60 degrees is the same thing as the co-function for sine, which is cosine. We're not talking about reciprocals here. We're talking literally taking sine and putting co in front of it. We're taking tangent and putting co in front of it. Now, those just happen to be reciprocals, but sine and cosine are not reciprocals. They're called co-functions. So all this is saying is sine 60 degrees is the same thing as cosine of the complement of 60 degrees, which would be 30. Okay, just do another one. Sine of 10 degrees is the same thing as cosine of 80 degrees. All right, so these angles have to add up to be 90 degrees, and if they do, then sine of one of those angles is equal to cosine of the complement. And then this is just showing how it goes the other way, of course. Cosine of 50 degrees is the same thing as sine of 40 degrees. Okay, so you just make the complement over here on the right and use the co-function. And it works with tangent as well. Tangent 15 degrees is the same thing as cotangent 75 degrees. 75 is the complement to 15. They add up to 90. Okay, and it goes the other direction as well, of course. Okay, so those are co-function identities. And then one more list of identities that sometimes prove useful, negative angle identities. And so this is just saying that sine, for example, of negative 60 is the same thing as the opposite of whatever sine positive 60 is. Okay, so if you were to look at the unit circle and look at 60 degrees, you would see that, or let's just go to the negative direction, negative 60 degrees is negative square root of 3 over 2. Okay, just looking at your unit circle, go down to 60 degrees, and that particular ordered pair is 1/2 negative root 3 over 2. Okay, so sine 60 degrees is negative root 3 over 2. Well, if you were to go up to the positive of that ordered pair is positive 1/2 positive root 3 over 2. So sine 60 degrees is positive root 3 over 2, but this says just multiply by -1, and you have the same thing. So that's really all that is saying. And that's also true for tangent. You'll get into this more in pre-calculus, but sine and tangent are called odd functions. If you notice, they act the same way. Tangent of a negative angle is the same thing as the opposite of tangent of the positive. Now for cosine, it's different. It's considered to be even. And the reason for that is if you were to go to, let's say, cosine negative 60 degrees, okay, so cosine negative 60 degrees, we'll just use that same example. That's 1/2. Well, that is the exact same thing as cosine positive 60 degrees, because up here it's 1/2 root 3 over 2. So those are the same. All right, so those are called negative angle identities. They're not used maybe as much, but useful nonetheless. So let's get started then with some homework examples. Your first block of problems will primarily be using those Pythagorean identities. So let me get to your page, and I'll give you some specifics just to kind of guide you in your homework. On page 658 is where your homework problems are located. Basically, big chunk of them, 9 through 20, are primarily going to be using those Pythagorean identities, and that's just going to help you get more and more familiar with them. Okay, so first of all, we're told that this angle theta resides between 90 degrees and 180 degrees, and so we need to pay attention because that's describing quadrant 2, and we're trying to find the answer for cosine, and cosine happens to be negative in quadrant 2, so our answer has to be a negative value. So since I'm looking for cosine and I'm given sine, this is a perfect opportunity to use this particular Pythagorean identity that has both sine and cosine involved. Okay, so I'm showing the identity, and now since sine is 1/4, sine squared would be 1/16. And now I'm just going to solve for cosine. Okay, subtracting 1/16 from both sides, you can think of this as 16/16 minus 1/16, that's 15/16. And now I'm going to do the square root of both sides, and normally we would say plus minus, but we know in this case our answer is just going to be negative. So I'm just going to do square root. Now your answers have to be simplified radical, no decimals, reduced fractions when possible. So I just did the square root of 15/16. I can't simplify the radical, square root of 15, but I can do the square root of 16, which is 4. And then the only thing left to do, again, remembering that I'm in quadrant 2 with this angle, my answer should be negative. And so there's my answer for number 1A example. All right, let's try another one. Find the exact value of cosecant if you're given cotangent. Well, that just happens to look a lot like one of our other Pythagorean identities that we came up with earlier. Cotangent squared theta plus 1 is equal to cosecant squared theta. All right. Cotangent, if you square negative 3/5, you get 9/25 plus 1. And you add these together, this is 25/25. So 25 plus 9 is 34/25. Now let's go back to where theta is. Between 270 and 360 is quadrant 4. We're looking for cosecant, which is the reciprocal of sine, and sine and cosecant are negative in quadrant 4. So our answer needs to be negative when we're done. Okay, square root of both sides. The square root of 34 doesn't simplify. The square root of 25 is 5. We came up with cosecant theta, but then remembering we're in quadrant 4, that makes our answer negative. Okay, 1C, again, find sine if you're given cosine. So once again, I'll just keep putting these in front of you. The more you see them, the more you do them, the more familiar they become. So this time I'm going to try to find sine given cosine. So sine squared theta plus 1/9 is equal to 1. So this is 9/9. So 9/9 minus 1/9 is 8/9. I'm in quadrant 4 again, so I'm looking for sine between 270 and 360. That's quadrant 4, and sine is negative. So I've got to make sure my -1, but just negative. Got to make sure my answer is negative when I'm done. All right, so square root of both sides. The square root of 8 simplifies as 2 times the square root of 2, and the square root of 9 simplifies as 3. And then since I'm in quadrant 4 where sine is negative, I need to make my answer negative. And so there's your answer for 1C. And then 1D, find secant if sine is negative 2/7. I don't have a Pythagorean identity that couples these together, but I do have sine and cosine just happens to be the reciprocal for secant. So I'm going to go back and use that same identity, and then when I get cosine, I'll just flip it over, and that'll give me secant. All right, so here's the identity again. Sine is given, so sine squared would be 4/49. Let's notice what quadrant we're in. So between 180 and 270 is quadrant 3, and sine and cosine are both negative in quadrant 3, along with their reciprocals. So this is 49/49 minus 4/49 is 45/49. Now I'm going to do the square root of both sides, and the square root of 45 is 3 times the square root of 5, root 9 times root 5, and then the square root of 49 is just 7. And of course, that would be negative. But again, we don't want cosine, we want secant, so we just flip this over and rationalize. Or you could flip this, you don't have to flip over the radical form, you can do either way. Either way, you're going to be rationalizing. Okay, so to rationalize, you just multiply by the radical, top and bottom, 7 root 5, and then root 5 times itself is 5, and 5 times 3 is 15. And again, it's still negative since we're in quadrant 3. So that ends up being your answer for example 1D. Okay, so we got a few more chances. This would be like your problems 21 to 26. So in this case, we're going to take a, well, I would say complicated or complex trig expression, and we're going to boil it down into just one trig value, one trig function. Okay. There isn't, I told the class, there isn't just one method for doing this. It's not a one-size-fits-all process because every problem is a little bit different. I would say this, though, it's a pretty useful strategy if you can. You can't do it 100% of the time, but if you can, just convert everything into sine and cosine and then simplify from there. So that's what I'm going to do here on letter A. I've got sine theta being multiplied times cosecant. Well, another way of writing cosecant is 1 over sine, because that's one of our reciprocal functions or identities. And then cotangent, it's one of our quotient identities. Cotangent is cosine divided by sine. Okay? So in the numerator, I'm multiplying sine times 1 over sine. Anytime you multiply something times its reciprocal, the result is 1. And then I'll just bring this down. So I'm dividing by this fraction, which means anytime I divide by a fraction, I'm multiplying by its reciprocal. All right, and so now sine divided by cosine is another way of saying tangent. So 1 times tangent is tangent. And so I told the class the process from getting to that single trig value from the original problem needs to be evidence of the usage of identities. Okay, don't just make me assume that you know that how to get from point A to point B. More is more when it comes to these problems and showing identities. And the more you use them, the more familiar they become. Okay, so for letter B, I'm going to do the same thing. I'm just going to convert this into terms of sine and cosine. So tangent is sine over cosine. And that's being multiplied times cosecant, which is 1 over sine, minus 1. And then secant is 1 over cosine. Okay, so multiplying up here, since I'm multiplying, I can cancel these diagonally here, so I'm left with 1 over cosine squared. theta minus 1. And I'm dividing by 1 over cosine squared, and kind of like we did up here, dividing by a fraction means to multiply by its reciprocal. Okay, so I'm multiplying cosine squared theta really times both of these, and so I need to employ the distributive property. So cosine squared times 1 over cosine squared is just 1. And then cosine squared times negative 1 makes negative cosine squared theta. And I'm just going to go back for a second. Remember, we had a Pythagorean identity, and I told you that you have some spin-offs. So remember how we made up these two red ones? And so they come in handy because cosine squared literally is 1 minus sine squared, and vice versa, sine squared. You can see that. So now, since 1 minus cosine squared theta is sine squared, that leads me to my final answer. All right, so let's move on to our last example. So letter C, once again, if you can, if it's possible, you want to convert things into sine and cosine. So secant is the reciprocal of cosine, so I could rewrite secant as 1 over cosine theta. And if you remember, going back to those original Pythagorean identities, I'll just jot this one down. Instead of going back in your notes, we came up with this one first. And so remember, sometimes it's beneficial to manipulate these and solve for one or the other. So if we just subtract cosine squared from both sides, we get this. So what this is saying is sine squared theta is the same as 1 minus cosine squared. So you literally can do substitution. You can replace 1 minus cosine squared theta with sine squared theta. And since you're multiplying, then you can do some canceling. That just becomes 1. I'm dividing by sine theta in both cases, so this just becomes sine theta instead of sine squared. So now I'm going to multiply 1 over cosine theta times sine theta. And that gives me sine theta over cosine theta. And that's a quotient identity. That's the same thing as tangent theta. So your goal is to take this original and bring it down into just one trig function value. And I believe that's it. That is the lesson. So I hope these examples help you as you work on the homework. If you have any other questions, feel free to let me know.